Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on January 2nd, 2026, just 4 days ago. It introduces a dynamic memory system that enables models to generalize to contexts of 128,000 tokens, despite being trained on sequences of only 4,000 tokens. The paper is titled FwPKM Product Key Memory, and as we'll see later, the results suggest a promising new path for continual learning in large language models. Alright, to set the stage, Table 1 contrasts the original product key memory with the new fast weight formulation. The classic approach, seen in the center column, uses slow weights that are frozen at inference, functioning essentially as a static, long-term semantic memory. The new method on the right, however, uses fast weights that update continuously during both training and inference. This fundamental change allows the model to act as an episodic memory, effectively mixing information across time steps to bind variables within the specific context window. Well, Figure 1 illustrates the architecture that makes this possible. At the bottom, the input hidden state splits into 3 parallel paths. The central branch drives the fast weights. A query interacts with the dynamic key matrices, highlighted in green, to select specific memory slots. These slots then retrieve content from the fast weight value matrix, shown in pink. Crucially, the system updates these parameters on the fly using the losses shown on the right, an addressing loss for keys and a mean squared error loss for values. This continuous updating allows the memory to instantly rewrite itself to match the current context. So, Figure 2 breaks down perplexity scores, where bars extending to the right indicate lower perplexity and better performance. In the center and right panels for LC64 and Lambda, the fast weight variants in darker colors clearly outperform the static baselines, confirming they effectively handle long-range dependencies. Conversely, the FwPKM results on the left show that standard static memory often drives the biggest gains for general knowledge. Crucially, the darkest bars demonstrate that combining both modules consistently yields the best results, suggesting they serve complementary roles. Alright. While Figure 2 showed the outcomes, Figure 3 reveals the internal dynamics by plotting gating value distributions. The horizontal axis tracks usage, where 0 means the memory is ignored, and 1 means it is fully utilized. In the rows labeled GDN plus FA, notice how the red density clusters heavily on the left. This implies that when unrestricted full attention is available, the model tends to bypass the new memory. However, in the rows with the PSWA suffix, the red mass shifts clearly to the right, confirming that restricting the attention window forces the model to actively engage the episodic memory. Okay, effectively engaging that memory leads to the results in Figure 4, covering the needle in a haystack task across contexts up to 128,000 tokens. The stacked bars track iterative reading passes. Dark blue is the first pass, while teal shows the second. In the first column, notice how that second pass triggers a massive accuracy jump, rising from under 10% to over 70%. Moving to the far right, while standard baselines drop to 0, the fast weight models maintain robust retrieval, proving they generalize far beyond their training limit. So, having seen the performance benefits, Table 2 now examines the computational price tag. First, look at the parameter counts in the first data column. Adding these memory modules explodes the model size from roughly 112 million to over 500 million parameters, reflecting that massive increase in storage capacity. Despite this huge size increase, the next column shows that the total compute, measured in flops, stays almost flat at around 22 trillion. This confirms that the sparse access pattern is theoretically efficient. However, the final 2 columns reveal a practical bottleneck. The samples per second drop from over 40 to around 16 for the fast weight variants, which the authors attribute to a lack of optimized hardware kernels compared to standard attention. Well, having analyzed the costs, Figure 7 now breaks down which design choices actually drive the performance. This ablation study tracks perplexity across 3 datasets, FwPKM, LC64, and Lambda, where longer bars extending to the right indicate better scores. Most variants hover near the baseline at the top, suggesting the architecture is relatively robust to minor changes in head count or normalization. However, the bottom row tells a different story. Removing the look-ahead values causes a sharp drop in performance across all tasks, identifying that predictive mechanism as the single most critical component. Wrapping up, 2 takeaways stand out. First, This architecture decouples training length from inference capacity, generalizing to massive contexts despite short training sequences. Second, by updating weights on the fly, it creates a functional episodic memory that complements standard semantic knowledge. This suggests a promising direction for agents that continuously learn without expensive retraining. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.